Today we're going to make a distance time graph. Distance time graph.
Yes, that's right.
And to help us, we've got our friend, the well-known jogger and keep fit fanatic, Mr. Sorry, what's your name again?
Mr. Grayson.
Mr. Grayson.
Yes, that's right.
Mr. Grayson.
Yes, I am a keep fit fanatic. Hurrah!
Well, off you go then. You measure the distance, I'll measure the time.
The jogger that we'd hired for the day began his run. My colleague, the professor, recorded the distance he moved, while I used a stopwatch to record the time. With this information, we could make a distance time graph. Distance time graphs can tell us a lot about the way an object is moving. We plot the distance on the y-axis and the time on the x-axis. We measured that he travelled 60 meters in the first 30 seconds. Plotting this as the point B and joining it to the origin, we now have a distance time graph. Let's examine what it tells us. I can see that our jogger is running at a constant speed of 2 meters per second. But how do I know that? Well, the fact that the graph is a sloping straight line tells me that the object is in fact travelling at a constant speed. That applies to all objects and all distance time graphs. Straight line, constant speed. So, how do we actually calculate a numerical value? Well, we have to remember that speed equals distance divided by time. To calculate the jogger's average velocity, we first read the distance, that's 60 meters, then the time, that's 30 seconds, and then we simply put them in the formula. Speed equals distance divided by time, so that's 60 meters divided by 30 seconds, and that gives an answer of 2 meters per second, showing full working out, don't forget that. Spot on, physics rocks. Now let us return to the nuclear test site and see what happens next on our exciting, thrilling jogging journey.
Thought I heard a bunny!
He seems to have stopped.
Yes, that's right.
Yeah.
Our upper-class friend didn't move for 20 seconds. This is easily shown on a distance time graph. The distance hadn't changed, it was still 60 meters, so we simply plotted point C. And look, it's a flat, straight line. It's horizontal. The object is stationary. It's not moving. He's going nowhere. On a distance time graph, we have a flat, straight line. Got it? Brilliant. Then suddenly, all of a sudden, he started to move again.
There you are, you little tinker. Come here. Now, come back. There he is, the bounder. Here, come here, buddy.
Yes, strange but true, but our tough keep fit fanatic seems to become obsessed with capturing some kind of unrealistic, inflatable, mythical rabbit. Meanwhile, we continued to accurately measure the distance and times that he was covering. And then, finally...
Yeah, got you, you bounder.
At last we could take our final measurements and complete our distance time graph. So, there we have it, our final distance time graph. And what does the final section show us? Well, between C and D, once again we have a straight line. This tells us he was travelling at a constant speed. But the line's sloping downwards. What does that mean? Quite simple, he's going backwards. He's going back to his starting position where this long journey began. And can we find anything else out about our mad toff? Well, yes, we can also calculate the speed that he went back to that original position. Why don't you try it? Have a look at the graph. During section C and D, what was the man's speed? You have 15 seconds to try and find the answer, and here's some lovely music to help you. Go. So, how many of you got the answer? Well, let's see. Between C and D, Well, speed equals distance divided by time. Between C and D travels 60 meters, and it took him 20 seconds. That means we have a speed of 60 divided by 20, which is 3 meters per second. Well done to those of you who got it right.
Anyone for a game of tennis?
All right.
You're rubbish at this.